Good evening, everyone, and welcome, or even welcome back to our Discover Our Universe series from the Kavli Institute for Particle Astrophysics and Cosmology at Stanford University. Now, we're coming to you live every 2 weeks with presentations all about the universe we live in and how it works. You can find out all about our upcoming events and watch all of our past talks over on our website at kipac.stanford.edu/discover. And you can watch this talk again later or any of our talks on our YouTube channel at youtube.com/kipac. We've got a lot of different topics coming up for you over the next couple of weeks. We've got talks on the dark universe, on some of the highest energy particles out there in the universe, the forthcoming Birrer Observatory, and the effect that the Starlink satellites are going to have on astronomy. But tonight, it's my great pleasure to introduce Dr. Simon Birrer. Simon is one of our Kavli postdoctoral fellows at Stanford, and he came to Stanford in 2019 after his first postdoctoral position at the University of California, Los Angeles, and after completing his doctorate in physics at ETH Zurich in Switzerland in 2016. Simon's research is all about why our universe is the way it is and the physical processes that made it that way. He's primarily using a process called strong gravitational lensing to learn all about dark matter and dark energy, and he's leading the efforts of an international collaboration of scientists to measure just how quickly our universe is expanding, while actively developing advanced computational and statistical tools that he makes publicly available to really push the boundaries of our knowledge. And tonight, we're very lucky to have Simon here to tell us all about bending space and time. Now, after the talk, we're going to have a Q&A with Simon, and I'm sure many of you will have questions, so feel free to submit those. If you're joining us on Zoom, head down to the bottom of the screen and hit the Q&A button, and you can send in your questions there. If you're over on YouTube, put your questions in the chat window, or if you prefer, I'm going to put a Google form in the chat links on both Zoom and YouTube if you want to send in your questions there. So do keep those questions coming in, and I'll hand over to Simon.
Thank you very much, Dan. Thank you, everyone, for joining. And I'm going to share my screen. So this evening, I'm going to talk about bending space and time, how we can use the phenomena of gravitational lensing to shed light on the biggest mysteries of our universe. So I will give a brief introduction of what this phenomena is of gravitational lensing, and give then a brief history of how it came to be one of the major players that sheds light in our universe, and how we can learn and push the boundaries with this technique. Before I get into the details of gravitational lensing, I would like to share another slide with a message that we have prejudices based on our daily life experience. So a lot that we do when we look out in the cosmos, we experience a lot of phenomena where there's no direct link of what we experience in our daily life. And so I would encourage you to take a bit of step back of what you're going to hear or what I'm going to tell you during this talk may be completely different than what you experience in your daily life experience. And one thing is also that we are here on Zoom or on YouTube, and many of you may be at a place on Earth where we are effectively upside down from each other. And that's the reality after all, but it's not how we normally experience our daily life. And through the exploration that humans have done over the past hundreds of years, I want to also share another picture. A famous one, it's already more than 50 years old, of the largest distance that humans have traveled from Earth, and look back at Earth and how tiny it is and what is the place of Earth in this large universe. And so this is as much as humans themselves have experienced the universe at large. And so without further ado, I go into a brief history of gravitational lensing. And the history of gravitational lensing is strongly tied to the history and the development of general relativity, our current theory of how gravity works, how space and time relate to matter, and how it's being curved. And so Einstein proposed this theory in 1915. So here a bit of sketch of Einstein and an illustration of what he meant if you have some matter and how space-time is curved around it. And most of the reaction then was effectively, this is crazy, this is not how things work, this is not our daily life experience, even from a scientific community at that time. And so it was new, it was different, and it was out of in space, literally. And so then the question is, how can we prove it? What can we observe to see whether this theory holds? And the first experiment that has been proposed and measured is using gravitational lensing. And so this was even proposed by Einstein himself at that time. And so what you see here is a sketch, not fully on scale, of our Earth here. Here we have the sun playing the role of the matter distribution that bends the light. And we have some star in the background on the sky that its light, when it's traveled towards Earth, gets bent around the sun. And when we look back and where we see it on the sky, it's up here. And so there was a clear prediction of how much the sun is actually bending the angle on the sky that the stars are being observed. So there's a problem here though, and the sun is so bright and the angle so little that the stars that actually get slightly perturbed are so close to the sun that they're nowhere visible, except in rare occasions when we make images like this one of a solar eclipse. When the moon is in front of the sun, the sky gets much darker, and the brighter stars on the sky appear. Here there's some marked near the sun. And it's that special time where the astronomers could measure the precise position of the stars when the sun and the moon were literally in front of it, and thus its position gets slightly bent. And then later on and earlier on, when the sun is not there, they can measure the relative distances of the stars on the sky. And they saw, well, here a sketch, wow, you're right. So this was effectively a first moment, a few years after the proposal of this theory, that there may be more on it, and we should look careful, should take it serious. So this is how gravitational lensing itself is closely connected of general relativity on one side, and also how this theory and this concept has been perceived by the scientific community at that time. So the title of my talk was not just gravitational lensing, but there's also the word strong in there. And so what is strong gravitational lensing in the context of astrophysics and cosmology? And here another simple sketch. You can think of it, this is a star, again, could be our sun or other massive object. And we have another bright source behind another star, and then the lensing happens. And in this sketch here, there is not one path that the light can travel towards us, but there are multiple ones. There is a second one down here where light can travel to reach us. And thus, when we look backwards, we see the object that originated here twice on the sky. So we see multiple copies of the identical object on the sky. And that's when we call it strong gravitational lensing. This has been proposed very early on when general relativity was introduced, that this phenomena can occur. First, more like as a theoretical playground, so to speak, but there was not a real life application or an astrophysical application or expectation that such an object or two objects could be real. Not until quite late, actually, in 1979, And so here this illustrates is a photometric plate of what's known as a twin quasar, the first extragalactic lens. I'll zoom in with more modern images and technique into it. And what you see here are effectively two objects on the sky that are very close in separation. And when the observer took spectra, meaning they disperse the light, they look at the imprint, how does the color of this object on top look like, and the one in the bottom, they looked identical in all aspects. And so there were twins, and it was confirmed that this is actually not twins, but it's a very same source being lensed by an object in its foreground. And this is an image from the Hubble Space Telescope, a more recent advanced space telescope that provides very high resolution. And what you can see here is effectively these bright point-like source quasars that's twice imaged. And what you see in the middle is a galaxy. And this galaxy itself, this yellow blob, forms what we call the lens, the compact matter distribution that allows to curve space-time in such that the light rays passing by wrap around and reach us from two different directions. So this was in 1973. There's a lot of analogy to gravitational lensing on the real life experience. And for that, I'll show you an image. So this you can experience yourself. This is a movie of fish, and you can count them, and you may find the number varies over time. And so gravitational or lensing itself can be described as a pure optical effect. And in the case of astrophysics and cosmology, the optical effect is caused by matter distribution. And here the optical effect is effectively the transition of the water that has a different diffraction index, so light travels with a different speed, and thus when it hits the boundary, it gets warped around as well. So all the phenomena that we see on the sky in that regard, or the images that I showed and will show, you can effectively reproduce in the laboratory or with an optical element such as a lens, or my glasses is also an optical tool that deflects the light such that I see much sharper. So this brings me to the Hubble Space Telescope. This was in early 90s, a space mission from NASA that really revolutionized a lot in astrophysics, in cosmology, and in particular, strong gravitational lensing. And the reason for that is because of its remarkable sharp images that allow to see close separation split images. And what this telescope provided us is a gallery of beautiful, what we call strong gravitational lenses. And here is such a gallery of what we call galaxy lenses. So what you see here is in yellow are massive elliptical galaxies that have a lot of matter there and thus curve space-time around it sufficiently. And these blue patches around it are other galaxies that sit in the background behind the massive elliptical galaxy. And it's like it's distorted around and wrapped around. And what you see here is not single dots, twice or multiple times. It's an entire shape of the galaxy that gets wrapped around, and what is known as the so-called Einstein rings. As you see some beautiful ring-like structure around it. And here's a movie how these light rays propagate through the universe, getting bent around a massive object. And then when we look right in projection to it, we see the wrapping of the source itself. another image. So here I have the pleasure to show you beautiful images of the Hubble Space Telescope. What you're looking at here is a cluster of galaxies. So you see a lot of yellow dots, larger, smaller ones. And this is a cluster, a galaxy cluster, a formation of galaxies that together are bound by a very massive structure. And so it's a collection of these galaxies that lead to even a larger, more massive structure, and that lead to even more bending and curvature in space-time. And in its background, you see different sources that have these stripes here. These are so highly distorted in one direction, leading to these strong arc-like features. And you can, and some of those appear multiple times in this image, and you can make a nice play of it where you find all the counter images that you expect to appear. So gravitational lensing, we can observe. It's a real thing. It's predicted by general relativity, and we see it actually being happening on the sky. And it has also another phenomena attached to it, which is the light travel time. So the number of, or the time passed between reaching us in one source or the other varies. So here is an illustration of another galaxy cluster and a source in its background, which is this spiral galaxy here, which appears here, which appears here, which also appears over here. It's the identical galaxy. And what happened here was a very rare phenomena. This is the year 2015, not so long time ago, where Hubble looked at this galaxy cluster, and it found these four blobs appearing in the image. And these four blobs here, a zoom in of it, this is an exploding star, what we call a supernova, which effectively outshines the entire galaxy that it sits in. And we see it appearing multiple times. So this is one single supernova that we see 4 times appearing. But we don't see it in this image, and we don't see it in this image either. So we only see it in one image. And the reason is the time the look back time when we see this image is different from the others. So what happens here is, here's a geometrical sketch, a slice, so to speak, through the universe with a zoom into this object. And the light travel time that it required for the photons to travel through the different parts of the galaxy cluster is different. So you have path difference, and this path difference are significant. So we're talking about cosmological scales, and so this can be months or even years different time. So this light has a finite speed. It's the speed of light. It's super fast. But on this cosmological scale, the relative path difference can result to significant delays, so to speak, when you when the photon reaches us from one or the other images. And we can make predictions about when this supernova will be seen in the other images. And sadly, so to speak, the predictions are for these 2 components in the past. So here I was not even born at that time when the supernova was expected to be visible at that time at this object. This was the supernova that just showed. And luckily, at least, we cannot time travel in the past, but we may revisit this object in the future, or in the time period of 2015 to basically now, that we expect the reappearance of the same supernova. So from seeing the supernova exploding in this image, knowing that it's effectively the same galaxy as we see here, with a clear expectation when the supernova goes off in this image. And not by surprise, we had a déjà vu. We had an event that we already saw in this, that happened in this part of the image. So here in January 2011, there was no blob visible. And then in December 2015, we see this blob appearing and the supernova basically going off. So we effectively invented time travel, so to speak, or a very good prediction of what happened in the past. So these are a story of phenomenology of what strong lensing gives us with beautiful images and phenomena we can observe that we can describe with our current theories. And what I want to glance into now is looking into the current mysteries that are still there despite all the successes that we have on the observational front. And I'll show you here some news articles, so to speak, that I cut out from the internet that say tension over Hubble constant continues, Hubble tension headache, clashing measurements make the universe expansion a lingering mystery, and other catchy titles when you Google Hubble constant tension will appear, many of them more recent too. And when you Google, you may also find press articles that have titles like "Quasars with double image gravitational lens could help finally figure out how fast the universe is expanding." And what you see here is a gravitational lens. And you may even see more articles with other gravitational lenses that are associated with this tension or the measurements around the Hubble constant. And so there's definitely something going on currently in the scientific community that causes some headache. And I want to go a bit into the details and then come right back into what strong gravitational lensing may tell us about this mystery. And to do so, I go back a bit in history, back in the year 1929, when Edwin Hubble and Georges Lemaitre discovered effectively that objects that are far more distant from us are traveling in respect to us further away. So they move further away. And that's a very unintuitive observation, so to speak, again. So prejudge this, everything. This is challenged the view at that time. That effectively the universe is expanding and everything that we look at is effectively moving away from us. And the further away objects are, the faster they're moving away. And that's effectively this curve here in this diagram. So this is the only data plot I show, and this is back in 1929. And the picture here that's being established also through general relativity is an expanding universe, and effectively that the scales, effectively the grids of where you can think of in mind what grids where the universe is placed on is stretching itself with its evolution. And so this is balloon cartoon is one way to sketch it, kind of daily life experience, but remember the descriptions we have to describe the universe and expansion is not what I personally experience here on Earth. And so what it leads is a so-called cosmological redshift. So that things that are farther away, these are also further in the past as light travels, are, so to speak, redshifted, that the light has stretched in. Well, Einstein was right once again. So everyone was happy with such a picture. At least it's an uncomfortable one. It's not what we have in the daily life experience, but where we have a clear framework to work, to predict, and to operate in, and doing observations. And the closer the scientific community looked at the expansion history of the universe, they discovered other unusual facts, so to speak, that the data tells us. And one of them was in the late 90s, early 2000s, that the universe was accelerating in its expansion. And this was totally new. not really expected by many people, and was established through observation. That it's not just expanding. No, it's like recently it's even faster. The expansion rate is faster and growing. So how can we deal with it? Well, one way is, okay, we buy it. So there's clearly observational evidence for it. And this also works for Einstein, and many theoreticians were happy with it. And the data was just so overwhelming over the year. Here's just a collection of data sets that allow to pin down the relative expansion history. And there's a line through it, which is the model predictions, our current models that allow to remarkably well describe the evolution of the universe. Until. So there may be something that we're missing still. And I fast forward here to a plot, so to speak. How fast is the universe really expanding today? And the speed in which the universe currently is expanding is known as the Hubble constant. So this is effectively the same questions. What is the Hubble constant? Is how fast is the universe expanding, and very related to how old is the universe itself, and how far away are certain objects. And this is 1929, and this is August 2019, so almost a year ago. So where different measurements indicate different values of the Hubble constant in regard of what this line prediction was through the plot that I showed you before, which were effectively measurements, or the line comes from imposed values around 67, while what we call late or local measurements indicate that the value is around 73. So what's going on here? And the answer is we don't know. And when you go Google Hubble constant tension again, you have other like half-dark forces been messing with the cosmos here from the New York Times. And what we really need to do here as a scientific community is work hard, make measurements, make different measurements, cross-validate our measurements, re-evaluate our previous measurements, and do it in the way such that we can firmly get to the bottom of whether these measurements provide us with new insight of something that we didn't know currently, or we don't know currently about our universe, or were there some remaining systematic uncertainty in some of the measurements. And here I come back to strong gravitational lensing. And so before I showed you predictions of when the supernova is gonna appear in the future or had appeared in the past. And now we can turn that around. We can, when we know when they appear, we can make predictions about how large the universe is and how fast the universe is expanding. So in that sense, measuring a time delay leads to predictions of the expansion rate. And this is known under time delay cosmography. So here's the next slide. This is supernova that is multiple imaged. What you have here is what's known under the name quadruply lensed quasar. So this is a massive elliptical galaxy that warps a background source around it. And this background source has a quasar in there. And a quasar is a supermassive black hole that is accreting gas that's in its process of accretion gets heated up and so hot and so dense that it outshines the galaxy in its brightnesses. And the good thing is this is not a static source. This quasar is fluctuating. And that's what you see here on this image. You see it wiggling, fluctuating. And these fluctuations allow us to measure the time difference between when a certain fluctuation appears from, say, the image up here relative to the image down here. And there's dedicating monitoring campaign where we're using telescopes to measure this time lag. And that's illustrated here. So this is one of the telescope, the collaboration that I'm heavily involved is using. This is a 2.2 meter telescope in Chile that is pointing effectively every night at a certain object, as long as it's on the night sky, and make measurements of the brightness of different images, so A, B, and C, and then plots the light curve, so we can measure how the flux is changing in each individual images. And one has a time lag versus the other, and you may already see by eye, you can measure the time lag or estimate the time lag, say, between the red curve and the blue curve, as they are coming from the same accreting source again. And this allows us to measure the time delays. So, and this technique is being used, and this was one measurement that is on this plot that I showed you before. Here's an update, July 2020. This is very recent. Effectively, the same questions, the same plot here from 1929. And in this plot here, there's one update, and this is the green measurement that previously was over there, moved down here and widened its error bar. So this is a team that I'm working on, and this particular measurement I led in the team. And here we revised our measurement and our technique, how we approached this measurement from the past by improvements, learning of what are known and unknown systematics, things we had assumed that may or may not have been true to that degree. And so this is an update in our measurement. And so the message I have here for the people listening, science is progress, and sometimes it's two steps in front and then one step back, and it's a constant iteration and revision of how we do the measurements, what data we collect, how we analyze it, is what we do robust enough. And in particular here, the questions are the stakes are big. So it's really, there's no direct theoretical argument why all these measurements should be high. That can be true. And if so, then there is a need of multiple independent, robust measurements that clearly tell us we need to change our current view and description of how we describe the universe at large. So this is the Hubble constant tensions from my personal perspective now. If I were to give this talk in a year from now, you may already hear me talking differently about it. It's a fastly evolving field, and I'm very excited to be part of it and to see where this is going to evolve in the next couple of years. So watch out, the news that's definitely are going to come. So this is on the expansion history and what strong gravitational lensing can contribute to it. I change a bit gears now for the last part of this talk into another aspect, and I show you another news article of a collaboration that I'm involved in. So here the title is 8 new quadruply lensed quasar lenses aren't just gorgeous, they reveal dark matter's temperature. So let's digest it a bit. So first let's look at the images. So these are quadruply lensed quasar. I've shown a few. So these are very similar objects that we know and love on the sky. Yes, they're gorgeous, indeed. And what they here, the title say, they reveal dark matter's temperature. They tell us something about dark matter. And indeed, gravitational lensing itself is sensitive to all the matter that is out there. And that's matter like the sun that we saw in the very beginning of this talk that deflects light. This matter can be gas. This can be entire galaxies. And this can be dark matter, which makes up most of the universe. It just doesn't shine and taste or smell in any regard that we can measure it on this here on Earth so far. And a picture of what we from theory expect dark matter to look like, if we could see it, is something like this. So we have a galaxy here in the center, it can be our Milky Way, and it's surrounded by what we call a dark matter halo. This is the the potential where this galaxy is sitting in, it's dominated by dark matter. And within there is a lot of granular structure that has been formed. So this is a computer simulation, and I also encourage you to watch Risa Wexler's talk, where she goes into details of how these simulations are made also here at Stanford. So these clumps are potentially there, but we cannot see them, except if we let light travel past through them. And there it comes back to strong gravitational lensing. And I show you here a sketch that has a lot of information. I'm gonna just one after the other walk you through this cartoon. So here on the right, you see real data of Hubble Space Telescope imaging, where we have here a massive elliptical galaxy, here two companion galaxies. These form what we call the lens. And it's distorting a background source, so something that's behind it, and that leads to this Einstein ring that you see here, this one side of the arc, and here's another counter image of it. And what you see here strikingly is this G4 object, which is also a yellow blob, which is very similar to this G2 or G3 blob. It's part of that group system of galaxies, so it's part of the lens itself. And this object warps and breaks here the smooth ring structure and leads to another double imaged part of the same source. So this is what we call substructure in the lens that further perturbs the features that we see on the sky. And so this is the data that we have. Then here in the middle, you see two different theory predictions of what dark matter may or may not be. And for these two different theory predictions, there are differences not just in the number of blobs but also how the imprint of light traveling through it is. So how often an arc gets disrupted. And this is regardless of whether these blobs are luminous or dark. And here on the very left side of this figure, what you see is that we know for sure that some of these blobs are associated with small galaxies. These galaxies are observed around our Milky Way and around local galaxies. That these galaxies have been discovered by large observational campaigns. One striking success here that I see of cosmology is that these little blobs here were predicted before these counter galaxies, so to speak, were actually discovered at these very faint, at these very little scales itself. And now the remaining task for us is to distinguish what is the physical origin of what we call dark matter. And to go into it, we have to look in the very details of the small scales of in the universe to see whether there are some remaining hints of what is the actual physical origin of what we call as a placeholder of dark matter. And this is ongoing research to quantify this very small structure and to learn from observations about what dark matter is or what it is not, what we can rule out, what theories we will, as we did often in the past, basically say, nice theory, we look at the data will tell us, is telling us a different story. And that's an ongoing campaign I'm involved. So the next slide here gives you a bit of hint of what we do, more on a daily life experience, so to speak, also with pretty pictures. On the left side, you see real data taken from the Hubble Space Telescope. And on the right side of it, you see a model prediction of the same objects, where we simulate the lens in the computer, and we are able to predict very accurately the phenomena on the sky that we see in the data. And this is a necessary ingredient in the steps that we are undertaking in measuring the expansion rate of the universe, in quantifying dark matter itself. And that's what we are now in the process of expanding and finding more of these lenses and doing all this analysis of it. And last but not least, I'll show you a famous image that you may not have attributed with strong gravitational lensing. Little spoiler, it is this one here. Has appeared on many front pages of major newspapers last year. It's from the Event Horizon telescopes, and it's the image of a black hole. And here the title of one here from the New York Times: "Darkness visible, finally, astronomers captured the first ever image of a black hole." And my first impression when I looked at it was, wow, impressive. And I've seen this. This is a strong gravitational lens. And the answer is, it's a strong gravitational lens and a black hole that plays the role of that strong gravitational lens. What you see here is, this is a radio telescope, so it's radio emission that's being emitted behind the black hole and then gets warped around such that when we see it in a ring, or almost a ring, which is effectively an Einstein ring, as a very same or similar phenomena of images that I showed you. Here, the difference is it's on much, much smaller scales. It's an incredible achievement what the team here did to effectively have, and here I did some Photoshop in the next part. They have resolved the smallest strong gravitational lens on the sky. So this is just like my personal view on it. And so next time you see this image, it's like, yes, it's a black hole, but it's also a strong gravitational lens. And with that, I just have my final slide and would like to thank everyone for attending, for watching, and looking forward to having your questions. Thank you.
Well, thank you, Simon, for what was certainly a talk bending my mind, let alone space and time. And we've certainly had a lot of questions from our audience about that. So just a reminder, everyone, you can still send in your questions for Simon. If you're on Zoom, just head down to the bottom of the screen and hit the Q&A button. Or if you are on YouTube, you can put your questions in the chat window on YouTube itself. Before we move on with the questions, just a quick plug. If you want to watch Simon's talk again, if you want to hear any of that amazing talk again, or if you want to see Professor Wexler's talk Simon talked about, or any of our other talks, they're all on our YouTube channel, youtube.com/kipac. So, our first question, so how big a telescope do we need to see these gravitational lenses and these multiple images of galaxies?
The Hubble Space Telescope is about 2.5 meters in diameter. It's a space telescope, and it's not just the size of the telescope that defines the resolution. It's one aspect of it. But the primary one here is whether the atmosphere is distorting the images and blurring them up. And so from the ground itself, when you watch, even with a 5 or 10 meter class telescope without additional guidance and support, you will not see the strong gravitational phenomena in that beauty.
So is this something we can do with adaptive optics from the ground, or do we really need to go to space for this?
Yes, we can do this with adaptive optics on the ground. So what is adaptive optics? It's effectively a high cadence correction in the mirror when measuring the fluctuations in the atmosphere to correct this blurring effect, basically on the fly while taking the exposure, to mimic almost a space-based, pure, no atmosphere imaging.
Sure. And I guess talking about space telescopes, I should ask you, is this something that really is the domain of Hubble, or is the James Webb Space Telescope going to help us here?
The James Webb Space Telescope is going to help us there. We are all very excited that I hope it's going to fly, launch, and take images in a year and a half from now. We're preparing extensively over years, so the community has prepared to see what kind of science we can do with it. A small word of caution, so Spain, the James Webb Space Telescope will provide us with a lot of insights. It will not provide us with so pretty images. So that part of like the optical images that we have from the Hubble Space Telescope, there it cannot compete. It has other aspects where it can look deeper to go for the earliest galaxies that have been formed and take a lot of information from these lenses too.
Yeah, great. And then for those of you who haven't heard of it, the James Webb Space Telescope is the next big observatory that NASA and our international partners are going to launch. And we're currently hoping to get that telescope off the ground in October 2021. So we're keeping our fingers crossed for that. And so many of the images that you showed of these lensed galaxies, they look bluish. So we had a question, is that an artifact of the post-processing, or are they really that color?
So there are two parts of it. So yes, there is post-processing in there. So every image that we see, even with our cell phone that we take effectively, has different sensors in there, detects different parts of the wavelength spectra, and then makes a computer in there that gives us the color that gets displayed of it. That's sort of like that part is to a certain extreme, yes. The intrinsic color of the objects that's being lensed are indeed bluer than the lens itself. So in that sense, it is close to the reality if we had ourselves a 2-meter Thales eye and watch them from space itself. And the reason for it is these galaxies behind are often very young, star-forming, very active, and produces a lot of very massive stars that are much or hotter, and thus when a star is hot, it shines mostly in the UV, so in UV ultraviolet spectra or blue, and less so in the redder one. And thus, when we see it more blue than the galaxy that is in front, which is what we call a passive, boring galaxy that has formed its stars many millions of years back, and has only stars mostly like our sun or less in mass.
Yeah, and I guess that's really showing the power of gravitational lensing as almost like having a giant magnifying glass on the universe that's showing us these really distant parts that the light has taken so long to get to us, that we really are looking at young galaxies and how we think our galaxy used to be when it was still growing.
Absolutely. So that's something I haven't mentioned here in this talk. That's effectively another magnifying glass, as you said, to look even deeper into our universe, to even zoom in on certain aspects that even with big telescope itself are barely accessible.
And so is it easy to tell if you're looking at multiple images of the same galaxy, or is there the possibility that maybe there's different galaxies in there creeping into these images?
Yes, and this possibility is pretty high. And the reason for this is that these objects that I showed, they're actually quite rare on the sky. So it really takes quite some chance that you have a very high alignment between something in the background and something very massive in between us, such that the multiple images appear. And about 1 in 10,000 objects is what we call a strong gravitational lens. And so most objects we look at are actually not strong gravitational lenses. And thus there's a lot of other things that can go on that we may have misinterpreted as strong gravitational lenses. And in particular here, if we look with Hubble Space Telescope on it, there's not so much ambiguities because the resolution is so high and the phenomena we can really describe of what's going on. But if we look at more fluffy, blurry, ground-based imaging data, there it's really it's hard to distinguish. And often we don't know until we put a lot of resources on that object. And then we finally know, and often we are disappointed. It was too good to be true. It's just a star next to another galaxy.
So if I can ask the difficult question then, so how do you make sure you're really confident that it is a lens you're looking at and they are the same galaxy imaged multiple times?
That's a great question. So for quasar lenses, where we have like bright point sources effectively that we have multiple images on, we can take a spectra, so we can slice the light of each individual component, and we see whether these spectra are identical. And then making the hypothesis that you have two exactly identical objects at this exactly the identical distance. And it happened to be that in the middle of it is a galaxy that may be the lens. There you have to run against many, many odds to deny the phenomena of strong gravitational lensing.
Sure. So you showed that fantastic picture at the end of the black hole, the first ever image of a black hole that I think I can speak for all of us when I say that we're just amazed in seeing that for the first time. So does the same lensing happen with a black hole? Is it possible to see these background galaxies and things bent around the black hole? Does it work in the same way, or do we see it in a different way around the black hole?
It works very similar. It's the same theory that is applied, so it's effectively the same. The reason why we don't see galaxies being bent around black holes is the sheer scale of it. So the scale of that image from that beautiful Einstein ring around the black hole is so small that even the images that I showed you with a Hubble Space Telescope cannot resolve those. So this distance is so small, it required effectively a telescope that has the size of the Earth. Literally, they had different telescopes on different parts of the Earth that together combined to create this remarkable image.
And is it possible that the light coming from our own galaxy can go out there into space? It'll be lensed around something, and can our light ever come back to us?
That's a great question. So part of the light may come back indeed when a photon that's been emitted by Earth travels very close to a black hole. It needs to be something that is really curving space-time so dramatically that it effectively passes by a black hole and comes back to us. There's just a lot that's going on around the black hole that this photons, this piece of light, is probably going to be observed or disrupted or absorbed, we call it, and that it's not passing right through it to come back to us. Yeah. And we cannot identify it. Yeah. So, but it's a nice dream, and there may be photons actually doing that. Yeah.
Yeah. Maybe one of the photons from the back of your head may come back to your eye one day. Yeah. But it's a big old universe out there, and there's a lot to get in the way.
Yes.
And so one of the most famous images is the Einstein cross. Why is it that the Einstein cross has 4 instances? Is there anything special about the number 4? Why aren't there more images or fewer images?
So the number of images has to do with the geometry and the asymmetry of the lens itself. So if you have a perfectly spherical lens, there is effectively only the solution to have a pure perfect Einstein ring of the image and a center image in between. And when you move off axis, you have one image on the left and one image on the right, which makes 2. And what you have is one tiny image in the center that normally is not being seen. So, and when you then have effectively a bit of an asymmetry in the mass distribution, you create another doublet and you get a quad, bright quad. And there is maybe 1 or 2 photons actually going through the center of the lens. And so it's actually 5 images. But the 5th very center one, we do not observe. There's the galaxies in the way, so that actually causes the lensing. So we unfortunately don't see it yet.
You have this sort of neat system then that you're essentially splitting each image into 2 each time, and then the 2 becomes a 4. But then it's unlikely that you're going to be able to split the 4 into an 8.
It's always odd images that appear, so that you can do mathematically. So you can split another pair of images to create from 4 effectively 6, but with
with the other one
plus the one in the center.
Yeah.
And that's how the hierarchy go. And when you go to cluster lenses, so when a lot of different galaxies play together to make up the lens, you get very complicated configurations that often we don't know how many images actually exist from a source.
So can we actually create maps of the curvature in space-time itself based upon the lenses we see?
We can generate maps based on model predictions, indeed, that match the observations. So that's a standard approach of ours to effectively mimic when I told the story about we can predict when a certain supernova reappears. This requires from us a map of having of what the lensing effect, what the bending and the curvature is doing. And yes, so we produce that in the computer. We cannot directly see it, but we can match these maps from the computer with what we see on the sky.
So moving on to sort of the consequences of these lensing observations for our understanding of the universe. We've developed this amazing picture that our universe is not only expanding, but it's accelerating. And that's coming out from all these different observations, including these lensing observations that you talked about. So I guess a couple of questions on that. So an important part of science is to verify our results and to constantly refine our understanding. So I wondered if you could just say a little bit more about that process and how long it takes to be confident in whatever measurement we've got to actually say that yes, these different values of the Hubble constant are a big deal.
If you look back in history, how in the past the field has evolved, it's normally of order a decade until something gets really established and that people can take it. And it requires a lot of effort from the community with different teams working on the same and different data until you throw a model overboard that before had done a remarkable job, and people have used it and found extremely useful in describing. And so here we may be in the midst of a process that may lead to a revision maybe in 10 years from now, maybe a bit sooner, but it's definitely not something that happens overnight, that you go in and next term you teach the class completely different. Even if you go back on like Einstein's General Relativity or any other major changes that happen, if you look back when these first papers appear and when it got taught in classrooms, there's a significant period that passes.
And with the universe accelerating, is the Hubble constant really a constant?
No, it's not, full stop. We call it the constant. The reason for it is when we call what we call now, tomorrow is obviously tomorrow. But in cosmological term, when we call it now, one day later or earlier in correspondence of like 13 billion years of evolution does not change any significant digit in this number. So it's evolving, but when people are going to measure the Hubble or the expansion rate in 100 years from now, they will not change a digit in the precision that we currently have and will have in 100 years.
So one of the consequences of the bending of space by material in it that causes our gravity is something called frame dragging, where if you have a black hole or something that's spinning, the space around it actually gets pulled around by that rotation. So you can almost imagine the space around a spinning black hole as being like flowing water that pulls anything in it around it. We had a question come in. Is that effect of frame dragging, is it visible in gravitational lensing? You said it's difficult to see this around black holes. And is it something that happens on the larger scales as well?
Good questions. On larger scales, so it's not present. So the regime we're working, so all the images that I showed, except that the remarkable one from the black hole, the optics and the physics we imply are are not in this what we call strong gravity regime.
Yeah.
So it's not when actually you see clocks ticking differently or wrapping of itself, what's happening around the black hole. So it's actually very weak gravity. And what makes it a strong lens is the sheer scale over which the phenomena happen, where the bending angle is very tiny. I cannot even make it with my hand.
Yeah. And actually, this is something I do in my own research, actually, is looking at the gravity around black holes. And we actually have other tricks up our sleeve to see this frame dragging effect. And one of them is actually when you're in that bit of space around the black hole that's really being dragged around, it actually helps save you from the black hole a little bit. You can stay in orbit when otherwise the black hole would have pulled you in if it wasn't spinning. So we do actually have tricks up our sleeve to see things in orbit around black holes. We can see very high energy X-ray light coming from that material being dragged around the black hole that shows us that the frame dragging is happening. We had a quick question going back to the talk of the James Webb Space Telescope earlier on. We just had a question, why won't it take as good a pictures as the Hubble Space Telescope? Is that because it's working in the infrared instead of in the visible light?
Yes. So for everyone that doesn't really understand what this yes meant, is that the telescope itself has a larger dish mirror size, so it is capable for the same wavelength to give higher resolution imaging or resolving power. The Space Webb Telescope was not chosen to operate in the same wavelengths as the Hubble Space Telescope. If it were, it would provide higher resolution images. It was chosen deliberately to operate in longer wavelengths, so more infrared, to look further back in time, literally when the first stars have formed. And these longer wavelengths is a trade-off in resolution itself. And so you go to lower resolution, build a larger mirrors, you get to similar resolution power than what we currently have with Hubble Space Telescope.
Sure. So it's just a limit really of being able to build a mirror big enough to get
Yes.
the same quality of image. And so back to the measurements of the Hubble constant. We had a question come in. Is there anything we can learn from the fact that some types of experiment come up with the smaller numbers of the Hubble constant and different types of experiment have bigger numbers? Is that telling us anything fundamental?
Yes. It depends on what assumptions these measurements made. So for example, if all the measurements that use local calibrators to measure the expansion rate locally, they all line up at a certain value, modulo its uncertainties that they all intrinsically have. And the others set of measurements are calibrated through, and now it gets a bit technical, pardon me, early expansion physics before effectively the cosmic microwave background has been emitted. So early universe physics of what how fast the hot plasma is effectively expanding and the sound waves within. And so if these two measurements do not match and don't give the same number, there is definitely, if this is decisively clear that all the local measurements give one number and the measurements based on the sound waves at the early universe gives another number, there is something either in between or in the assumption of how the predictions were made was off by several percent actually. And so there we need some ingredients to be added or changed in our model. And that's under debate.
So there's a lot we can learn about our universe from just that one number.
Yes, how old the universe is, for example, is a pretty direct prediction. So
yeah, so I think we've just got time for one more question. And so what breakthrough in astrophysics are you most looking forward to in the next 10 years?
I want to understand what dark matter is, what it's actually made of. Currently, there are a lot of models, what type of particle nature it may or may not be. Some of them have, in the meantime, been ruled out by particle physics experiment. We're in the process of constraining it further with astrophysical observation. And my hope is that in the not so far future, we actually find common ground on both sides from a particle physics perspective and from a cosmology perspective of what the actual underlying nature of this phenomena is.
So a lot to look forward to in answering those big questions. Thank you, Simon, and thank you everyone for joining us here tonight. If you want to see that lecture again or any of our past public lectures, they're all recorded over on our YouTube channel, kipac.stanford.edu /discover. There's a link on that page. We'll be back in 2 weeks' time on Tuesday, August the 11th, when Dr. Alex Amon will be talking about the dark universe. So don't miss that. And again, you can find out more about that over on our website, kipac.stanford.edu /discover. Well, bye-bye for now, everyone. Stay safe, and we'll see you again in 2 weeks' time.